So here are some recipes. There's around 7 of them that you would want to know in order to be able to synthesize the kinds of molecules that you may get asked about in this ether chapter. I'll make separate videos that explain how each of these reactions work, but for right now what you want to know is what the recipes are and what they do. So if you want to put a halogen onto an alkane, a carbon that has all single bonds, add bromine, Br2, and H-nu. Now this looks like a V, but it's actually the Greek letter nu, and that H-nu is just standing for light. So you'd be shining ultraviolet light, and you'd add some bromine molecules. If you want to create a pi bond, make sure you have a halogen to begin with, and then just add a strong base. If you want to create more bonds to oxygen, make sure you have an alcohol, and you're going to add Na2Cr2O7, H2SO4, and H2O. If you want to replace an OH with a Cl, then you make sure you have an alcohol to begin with, and then just add SOCl2. You can add a nucleophile to a carbonyl. A carbonyl is when you have a carbon double bonded to oxygen. You can add a nucleophile onto that carbon. The carbonyl becomes an alcohol. You can open up epoxide rings by adding a strong nucleophile. So here you have your epoxide ring, and the key that would tell you you would want to do that is that you'd have functional groups on adjacent carbon atoms. And last but not least, you can make Grignard reagents, which are really strong carbon nucleophiles, by taking an alkyl halide and adding solid magnesium. So those are recipes. Right now we're not going to worry about how they work. I'll make separate videos that show you how each of these reactions work step by step. You wouldn't be tested on that. What you will be tested on is using these reactions to transform molecules from something to another. For example, here, the question says, propose an efficient synthesis for each of the following transformations. And you're going to use the reactions that we just quickly went through to make that happen. Now, there are going to be a couple tricks, and one trick in this new chapter, this ether chapter, is that anytime you see functional groups on adjacent atoms, so here, for example, you see a functional group, this is on this one carbon, and on the carbon right next to it, you have another functional group. Anytime you have functional groups on adjacent atoms, it's a sign that you probably made it from an epoxide. So we'll take this, if we're trying to make that, we have a bunch of this stuff in our warehouse, and we're trying to make this because it'll save people's lives or make your startup company a whole bunch of money. We can make that from an epoxide, and the reason you would think that is because you have two functional groups on adjacent carbon atoms. So you draw the rest of the molecule completely the same. It's just those two atoms that had the functional groups on them are now two atoms in an epoxide ring. Okay, so looking at these, how could we turn a double bond into an epoxide? And we learned how to do that using MCPBA. That turns any double bond into an epoxide. The two atoms in the double bond become the two carbons in the epoxide ring. Then, once you have that, you can take a strong nucleophile. Now this oxygen in this ring ends up becoming the oxygen in that functional group, that alcohol. So the nucleophile we need is going to be the one that's not on there yet, the CN. So you can take a CN, and we need it to be a nucleophile, so it has to have a negative charge. And that's going to attack our epoxide. Oops. The carbons bonded to the oxygen are slightly positive. The oxygen itself is slightly negative because of its electronegativity. And so this nucleophile is going to attack the less crowded carbon. That's this one on the right. If you look at the carbon on the right, notice that it's bonded, this carbon right here is bonded to just 2 other carbons. So that is secondary. If you look at the carbon on the left, this one right here, it's bonded to 1, 2, 3 other carbons. So that is tertiary. And so the secondary one is less crowded, so that's where it's going to be easier for this to attack. If you're going to form, so this carbon here has 4 bonds. If you're going to form a new bond, one of them has to break. The one that breaks is the weakest one, the one that's already weakened by a separation of charge. And so those electrons go onto the oxygen there. You would end up with, the rest of the molecule stays the same. You would end up with, oops, the oxygen has the bond there still. And you'd have that CN. So we're pretty close to what we want. We just need to get a hydrogen on that oxygen. So what you can do is add water. When you add water, it gives a source of hydrogens for that oxygen to attack. The oxygen on water is slightly negative, the hydrogens are slightly positive, and so that oxygen on our molecule of interest can attack one of those hydrogens and steal it, and you'd be left with the molecule we want. So this. Okay, so the first thing you'd want to do here is add MCPBA. That turns the alkene into an epoxide. The second thing you'd want to do is to add this CN nucleophile. Now you could just write this, but most of the time what they'll do is instead of writing something with a charge, they'll write this with a metal. So something like sodium or potassium. That metal has such low electronegativity, it gives its electrons to the CN, and you end up with the CN with the negative charge. And then last but not least, just to add that extra hydrogen onto the oxygen there, you'd want to make sure to add H2O. Now, the answer to this is really just these right here. But if you have time, I would encourage you to draw the mechanism, because it would give me an opportunity to give you some partial credit. Whereas if you just draw this and it's wrong, it would be hard to give you partial credit for that, because there wouldn't be any reasoning present there. That would show that you knew principles behind the reactions. Just to see something a little similar, let's jump to C. We'll come back in a second. But notice here we have the same sort of landmark. We have functional groups, and they are on adjacent carbons. So they're on adjacent carbons there, and that is a landmark that tells you whenever you have that, you can make that from an epoxide. So just take those 2 carbons that had the functional groups and make them the 2 carbons in an epoxide ring. Then, how can you make this? We have an alkene to start with a double bond. How can we turn that into an epoxide? You would add a peroxy acid like MCPBA, and that would turn that into an epoxide. And then we just have to worry about turning this into our product. So you would do that by adding another nucleophile. Now the oxygen that you have here in the epoxide is the oxygen and the alcohol. So what we need to add is this SH. So that's going to be our nucleophile. And on the epoxide, the oxygen is slightly negative. The 2 carbons bonded to it are slightly positive because it steals electrons from them. The negative sulfide, that SH, that is attracted to the positive charge and specifically to the less crowded positive charge. So this oxygen on the right is bonded to just one other oxygen, so it is primary. This oxygen on the left is bonded to two other oxygens, so it is secondary, and you can see that primary is less crowded. So that attacks there. The carbon it's attacking this carbon already has 4 bonds. To make this new bond, it has to break one, and the easiest one to break is the one that's already weakened by difference of charge. The electrons go to the most electronegative place nearby, which is the oxygen, and you would be left with this. This would have had 2 lone pairs already, and the third lone pair is coming from the bond. So the only thing we're missing is that H there. You can get that H just by adding some water. The oxygen here is slightly negative, the carbons are slightly positive, and so this negatively charged oxygen steals one of those hydrogens. And you're left with the product you want. Okay, so the steps we went through to get that. First, we had to turn the alkene into an epoxide, and we did that by adding MCPBA, metachloroperoxybenzoic acid, a peroxy acid. Once we did that, we had to add our second functional group, and so an SH minus. Now, technically, you could just write SH with a minus charge. Usually, though, the way that's written is with a counter ion, so something like sodium. And because that's a metal, it gives its electrons away, and we get our sulfur with the full negative charge there. Now that almost got us to the end. We just had to add that extra hydrogen onto the oxygen there, and we did that by adding water. So the answer to this is really just these 3. But if you have time, and you may not, this green part is the priority, to make sure you write that. But if you have time, it would be nice to write out the mechanism so that just in case you get a couple things wrong, there would be an opportunity to give you partial credit. Okay, so we can take that same reasoning. Let's go back to B, which is a slightly more involved question. And at the very beginning, you see that same landmark that we've seen before. We have 2 functional groups, and they are on adjacent carbons. That is a sign that we should think about using an epoxide. The 2 carbons that have the functional groups would be the 2 carbons in the epoxide ring. Anytime you have 2 functional groups on adjacent carbons, you should think about making them using epoxides. And how do you make epoxides? Well, the way we've been making them in the last couple problems is from a double bond. But how? We don't have a double bond here. We would have to make a double bond. How do you make a double bond? You could make a double bond using an elimination reaction with a halogen. So this is what we need to do. Somehow we need to get a halogen onto this ring. Once we do that, we can do an elimination reaction. Then we can turn the double bond into an epoxide, and finally we can open that ring up. Okay, so let's start. We have an alkane. The alkane is very unreactive. The way you put something on an alkane is with a radical reaction. That's with Br2 and light. So the first mechanism here is with Br2. The first step is you need molecular bromine and ultraviolet light. And what ends up that this H nu is really coming from that's just the energy for light, if you remember from General Chemistry 1, is Planck's constant h times the frequency of the light, which is nu. H nu is just a shorthand for light. So you'd be shining a ultraviolet light onto this bond, and because the bromines have equal electronegativity, when the bond breaks, one electron goes onto one bromine, the other electron goes onto the other. And that creates two very reactive molecules called radicals. A radical is a molecule that has an unpaired electron. Unpaired electrons are really unstable. So this takes our alkane, and the first radical donates its electron, steals one from the hydrogen to form a new bond there. The other electron in that bond goes onto the carbon. Notice the arrows I'm drawing. If an arrow has two heads, it means you're moving two electrons. If it ever only has one head, it means you're moving just one. These one-headed arrows are called fishhook arrows. So that gives us our first products. The hydrogen and the bromine are now bonded to each other, and we have a radical on this carbon. So the other bromine swoops in, donates its electron with the one electron on the carbon, and that makes that puts the halogen on that alkane. So okay, we use Br2 and light to put the halogen on the alkane. Next, we would want to do an elimination reaction. Now you can do elimination reactions by adding a strong base. A strong base is any alkoxide. Here I'll just do sodium ethoxide. It's a pretty standard, strong, skinny base. So what happens here is you'd have this bromine here, and you have a hydrogen on an adjacent carbon. Now, NaOET, what is that? Sodium is a metal. It loses its electrons, becomes slightly positive. The oxygen it's bonded to becomes negative. And Et stands for ethyl, so that's just two carbons. The sodium goes off, lives its best life in the beaker. This negatively charged oxygen steals this hydrogen. Its electrons go toward the halogen and kick the halogen off as a good leaving group. And so that leaves you with the alcohol version of whatever base you had. Bromine floating around. And the most importantly is the ring you have. These electrons here go to form a pi bond. So if you have a halogen, like we did here, you can turn that into a pi bond by adding a strong base. And that would have been a whole chapter in Organic Chemistry 1, talking about how you can do that. Okay, so that's our second step. Now from here it looks pretty familiar. We have a double bond, we want to form an epoxide, and we do that by adding MCPBA, that peroxy acid. And once we have that, we want to open this ring. So let's say these bonds are coming out at us. I could have just as well said they're both going away. If they're coming out at us, what we've seen before is that this oxygen goes to form one of the alcohols. And so the other thing is the nucleophile that we need to add to open this ring up. So we need to add OH minus. Now, that oxygen is slightly negative. The two carbons it's bonded to are slightly positive, and so this OH minus is going to want to attack one. They're equally substituted. One isn't more crowded than the other. So it attacks one there. It's going to attack from the opposite side. So let's go through a detour here. It would attack from the opposite side. So if this one oxygen is coming up, It wouldn't be able to attack from there, it would attack from the opposite side, the side going away. So we're almost done. We almost have what we want. We just need to get rid of that negative charge, and as we've seen before, the way you can do that is with water. Oxygen is slightly negative, whatever it's bonded to is slightly positive, and so this negative oxygen here steals a hydrogen, and you get your product. Okay, so that's the reasoning sort of behind this. The answer to this is first, you add Br2 and H nu. That puts the bromine onto the alkane. Second, you need to add a base. I chose sodium ethoxide, NaOET. That rips the hydrogen off here, which kicks the bromine off and adds the pi bond. Once you have the pi bond, you'd add a peroxy acid like MCPBA. That turns the alkene into an epoxide. Then we needed our nucleophile. The nucleophile we needed was OH-. Usually you combine these with a cation instead of just writing the charge. We knew we had to add OH- because that was the thing besides the first oxygen that was on the adjacent carbon, the functional group that was on the adjacent carbon. And last but not least, just to make sure that that oxygen isn't stuck with a negative charge, we add water. So these 5 beautiful steps are the answer to this problem. That's how you could turn this ring on the left into the ring on the right. Okay, now for D, make a note, you do not need to know how to do this one. This is snuck into the homework here by accident. It's asking about something that we haven't had a chance to go over and that we didn't have a chance to go over in this chapter. So do not worry about D or how to do that. If you're interested in how to do it, you're more than welcome to come and visit me during my office hours. I would love to explain it to you. But you're not responsible for D or anything like it on your test. Okay, E, so the last one for this, these adjacent functional groups. So one thing that's kind of nice, they didn't just give us the alkene, so we don't have to form the epoxide, we have it to start with. But there's another thing. We could follow this oxygen and say, okay, that oxygen is there, but what's the thing that was added on the right side? What was the nucleophile that was added here? Well, whatever it wasn't drawn in, and the only element that you could have there that you don't have to draw in would be a hydrogen. We had a hydrogen nucleophile. So if you take this and we open it up with a nucleophile, that nucleophile could come in, attack, open that ring, and we could work from there. Now, you might be tempted to have something like NaH. That sort of follows the pattern that we've been using before. Unfortunately, though, this only functions as a base. The hydrogen is so small there that it's not stabilized enough to reach a nucleophilic center. It would just steal the nearest hydrogen nearby and bubble away. A nucleophilic hydrogen would have to be supplied by something like LaH. LaH stands for lithium aluminum hydride, and it looks something like this. You have aluminum in the middle, 4 bonds, 2 hydrogens. That whole thing has a negative charge, and lithium is balancing that negative charge. And what you'd want to notice about this is that you have a metal in the center. Anytime you have a metal, you have really low electronegativity, and the electrons go to whatever is bonded to the metal. Hydrogen isn't a particularly electronegative element, but compared to a metal, it is. And so And so hydrogen gains the negative charge by attracting the electrons in those bonds more, and it becomes nucleophilic. And this is a stable form. This stabilizes the hydrogen enough to allow it to act as a nucleophile. So you'd see this you'd name this as LAH, or you might sometimes see it as LiAlH4, lithium aluminum hydride. So these hydrogens would take their electrons, attack the less crowded carbon. Notice this carbon on the right here is only bonded to one other carbon, so it's primary. Carbon on the left is bonded to two other carbons, so it is secondary, so this one is less crowded. So it attacks that one, right? The oxygen here has a negative charge. The two carbons it's bonded to have slight positive charges. So the hydrogen attacks that carbon on the right. That carbon already has 4 bonds, so if it's going to form a new bond, one of the bonds it has to break, and that's the bond that's already weakened by separation of charges. So that would give us this, which is very close to the product we want. There are 2 things here. First, this has a negative charge, so let's get rid of that. And we've seen how we can do that by adding water. Water has a slight negative charge. These hydrogens have slight positive charges. This oxygen steals that hydrogen. And we have this, that alcohol. And so at this point, we have everything we need. We just want to form one extra bond to the oxygen. And the recipe for doing that is sodium dichromate and sulfuric acid and water. And the mechanism for this is really long. I'll explain that in a separate video. But to make that transformation happen, that is what you'd have to add. So, going back to our exercise here, if we add sodium dichromate, Na2Cr2O7, and sulfuric acid and water, then we get our product. So one step at a time, the first thing we did is we added lithium aluminum hydride, and that popped open this epoxide ring to get our product here. Then we had to neutralize that oxygen by adding water. So then we had our alcohol, and last but not least, we had to make that extra bond to oxygen. Making extra bonds to oxygen is called oxidation, so we did that oxidation with Na2Cr2O7, sulfuric acid, H2SO4, and water. Okay, so the one thing that tied each of the problems we did together is that each of these products we wanted to make had functional groups on adjacent atoms, adjacent carbons. And the one common feature that they had was, because of this, the way we created that was through epoxides. And everything else was built around that concept.